Okay, so the idea now is to talk on a R-type instruction in MIPS and how we convert this to its value in binary and hexadecimal. So you can see here a type of R-type instruction. R-type instruction are built, as you can see here, they start with an opcode, which is 6 bits, and then there is the RS, which is the register. Now note that this is not exactly in the order in which we write in MIPS the instruction. This RS, this register, is this 0 in here. Yes, so this is how it looks. This is the 0, it comes from the RS. And the RT is, again, this is a $3. And the RD, which stands for R destination, is the register that is right over here, because if you read these instructions sub u, it takes the 0 and it subtract from it the S3 register, the value in it, without signed value, so it's unsigned because of the U here. And the result it insert into the R destination, to the RD, which is this one. Note that the order in this instruction generally and how we represent the R-type instruction is not the same order. This RD is this one, and this RT is that one, and this RS is this 0. So note, this is not in the same order. Now, when we want to translate this instruction, R-type instruction, into its values, there are values for the operating code, what is called opcode in R-type, for the function. So the opcode has a value, the registers has a value, they have values, the shift have value, and the function have value. If we look here, you can see that the different types of registers have different values because they are numbered. So for example, 0 is now 0, 8 is 1, VFS is 2, and this is their, let's call it, I don't know to call it, numbering. It's not their value. I can insert different values to those uh, registers except for the 0 one. I can insert different values, but their code representation will be this. So for example, A1 is this one. So we have, for example, S3, so here it is. So its value is 10011, right? So we have also T0, so T0 will be right over here. It's 01000, and we'll have 0, which is uh, okay, 0 is a representation of 0. And what else? We had sub u. Sub u, let's see if we find it here. I don't see it right over here. Here it is here. So its binary is for its function. Its opcode is 0, but its function is 100011. Remember that in R-type instruction, always the opcode is 0. So if we go back to our instruction over here, the opcode will be 0 in 6 bits. So 000 is right over here. The RS, which here is 0, will be just zeros. Here it is, because this is 0. This is how we translate it. The RT, which is this one, this register S3, will be, as you saw in the table, its representation is 00111. Of course, I can insert, when I do a program in MIPS, I can insert different values to S3, but its representation as in the instruction will always be 0111. Yeah, 00111, as it right over there. So it's this one. Now the next one is the R destination. Again, it's this one over here. So T0, here it is as you saw in the table 01000, which is, you can translate it. Okay, so the next one is the shift. So this is only for the shift. How much we want to shift for shift. Okay, for example, shift left or shift right register or something. But this instruction right over here is not using shift, so it's not relevant over here. So I just put 5 bits of zeros like this. And the function value, as you saw in the table for sub u, is 10001, which is 35, which is, I can translate it to hexadecimal. So now I can just take those binary values, and this is how the function is, the instruction is, this R-type instruction is represented in binary. I can do a continuous binary, which just removing the spaces. I can translate each of them to decimal, as you can see here, 0, 0, 0, 0. This is 7, this is 8, this is 0, this is 35 in decimal. And I can do the same for hexadecimal. This is 0078. Now 35 in hexadecimal, we need to translate it to, in decimal, we need to translate it to hexa. So we divide by 16. The value is 2 with a remainder of 3. So we continue with the 2, divide by 16. We got to 0 with a remainder of 2 again. So the number will be 2, 3. So the hexadecimal 35 is 23 in hexadecimal. Okay. So in hexadecimal, I can just put 0078023 as I did just right over here. For each part of the instruction, I just wrote what is its value. Now I can also take the binary representation of the instruction and translate each segment of it to its hexadecimal value of all of this. So I just divide it to fours. I mean, each 4 digits will be translated to one value in hexadecimal, right? So remember that 4 digits in binary can get up to 15 in decimal. So 4 digits in binary represent 1 digit in hexadecimal. So here it is. I take this binary and divide by 4. Each 4 I took separately. 4 here, the next 4 is this one, so it's right over here, and just like this continuing, and I get this one. And now I translate, this is 0, so I write it here 0, this is 0, I write it 0, 0, 0. The next one is 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, which is 4 plus 2 plus 1. Oh, 0, 1, 2, 4 plus 2 plus 1 is 7. I need it. So this is not true. Should be 7. And this is not 8. 0, 1, 2. This is 4. This is 0, 2, and 3. Great. So you saw how I translated it to hexadecimal. Now in base 4, what I will do, I take this continuous binary number and divide every, remember that every 2 digits in binary translate to 1 digit in base of 4. So I will just separate this value for twos, for pairs of binary, and this will present me, and it will be very easy to translate it to base of 3 or 4, because after I separated all the numbers. What I do is just take this, we start with this one. This is 0, so I write it 0, 0, 0, 0, 0, 0, and here is 1, and then here is 3, 2 to the power of 1 plus 2 to the power of 0 is 3, 2 to the power of 0 is 1, and 0, 0, 0, 2 to the power of 1 is 2, and 0 and 2 to the power of 1 is 2, plus 2 to the power of 0 is 1, so we get 3. So this is how I took a instruction, which is an R-type instruction, and walk throughout it and represent it to its ingredients as an instruction in MIP, which includes the opcode, the RS, the RT, the RD, the shifting, which is SHAMT, and the function. And you saw how I use tables to define what is the code for each element of this R-type instruction. And remember that the opcode for R-type instruction is 0, and shift shunt will be used only for shifting instruction, which this one is not. And remember the order, which is not like we see here. RS is this, RT is the one that is the order, the register that is here, and the R destination is the one that right over here. So the order is not like you see on the actual instruction in MIPS. Okay, so and remember that all the instructions in MIPS are 32 bytes. So if you count it, this is 6, 5, 5, 5, 5, and 6. It should, yes, it is 32 bits totally, and this is what should be for each type of instruction. We have R-type instructions, J-type instruction, and I-type instruction. Those are the main types. There are some more, but those are the main types: R, I, and J. R for those instructions, I for immediate, and J for jump instructions. That's it. Thank you very much. If there are any mistakes or correction, please tell me, and that's it.